Okay. Hello and welcome to Oxford Energy Society's Week 2 talk on how we can achieve a zero carbon future. I'm joined here by Chris Goodall. Chris is the author of several successful books on new energy technologies and sustainability. He's a businessman, speaker, and owner of the website Carbon Commentary, which, alongside other things, produces a weekly newsletter covering energy technology and finance. Today, Chris will be speaking to us about his latest book, What We Need to Do Now for a Zero Carbon Future, which was shortlisted for the 2020 Wainwright Prize for Writing on Global Conservation. So now I'll hand over to Chris. So by all means, Chris, take it away.
Okay, thank you very much indeed, Ben. Thank you very much, everybody, for inviting me. I said to Ben earlier a few minutes ago that these things work so much better if we try to get a conversation going. So please interrupt, ask the questions, prompt Ben, shout at him. We need to make this more lively than the typical Zoom presentation that you're experiencing in your tutorials at the moment. I'm just down the road. I live close to St Hugh's College, and I've benefited enormously over the years from the academic seminars that the Oxford Energy groups, the various Oxford Energy groups organise. And this book comes partly out of that. What we need to do now has a very simple objective. It tries to provide a route to net zero across the UK economy and society. I don't specify a date in the book, but speaking personally, I think 1.5 degree temperature rise is probably requires us, the world as a whole, to get close to net zero by 2040 at the latest. Obviously, there's continuing arguments about that. Nobody's quite clear what climate sensitivity is, but the fact is that 2050 is probably too far away, and pretty much everybody would now agree with that. The second objective in the book is to show how, at least in outline, because it really is, it's a short book, it doesn't give a detailed plan, it's an attempt to illustrate what's possible and what isn't possible. I attempt to ensure that the effect is positive on the less well-off. One of the reasons why I think it's been difficult to secure action across the world on emissions reduction is that it's been seen, the process of emissions reduction has been seen to be inherently disadvantageous to the less prosperous. We have to change that. And in every chapter of the book, I propose routes by which that might happen. Now, I suggested that I talk in total for a maximum of 40 minutes. So that means that if the whole thing takes an hour, we need roughly 20, 25, 30 minutes of questions and discussion. So please do dive in. But final point on this slide, I want to show to people who probably aren't very much involved in the issues at the moment that decarbonisation is possible, and probably that it's advantageous to a society like the UK. The book is predominantly about the UK, but I try to use examples from around the world where actions by other states are more rapid, more effective, more ambitious than the very limited and disjointed proposals that have come out of this current government, which for the last 4 years obviously has other things to worry about. But come January the 1st, we really ought to be looking out for this as our principal policy objective for the UK and its society. What we've done so far in our attempts to move towards net zero, when we've made considerable progress in the UK since 1990, the date of the Kyoto Accord, is to focus on electricity generation, which was the most important sector, and in many countries still is the most important sector from a point of view of total emissions. So of the total of 450 million tonnes or so, I can't remember the exact number, for declared UK emissions, which of course emits the emissions that come from our imported goods and things like international shipping and aviation, we've cut the percentage that coming from electricity down to probably very little more than 10% this year, as we've moved away from coal and increased the percentage of gas, but also massively improved the percentage of renewables, including biomass and nuclear, on our grid. And at the same time, of course, electricity demand has been tending to go down up to 2-3% a year as we get more efficient in our use of electricity and have essentially deindustrialized in that 30-year period. So electricity now not particularly important, and it's being taken over by lots of other things, of which the most important is surface transport, cars, lorries, to you and me. Now, electricity, therefore, is a tiny fraction, or a very small fraction, and falling fraction of total emissions from the UK economy. So the book looks at various other things that we need to worry about over the course of the next 20, 30 years as decarbonisation goes on. This mixes agriculture, fertiliser production, beef, heavy lorries, housing insulation. I'm sorry, this is not moving as fast as it should do. There we are, that's back on there. Housing insulation, an absolutely critical thing for the UK. Our houses are amongst the leakiest in Europe. 3 times approximately as leaky as they are in Germany per degree temperature difference per square meter. We have to worry about cement and steel, aviation, of course, and long distance shipping. Both of those responsible for 3 or 4% of global emissions. Steel possibly 7 or 8%. Cement 2 or 3% at least. And of those other ones, of course, we're going to talk about energy, but also about agriculture, which is, depending on how you calculate it, depending on whose figures you believe, roughly 25% of the global emissions problem. Now, I'm going to talk...
We've had our first question. It's from Paul's Forthout, and he says, is it a dangerous distraction to talk about, i.e. the rate of reduction?
Sorry, Ben, I didn't hear you. Could you say that again?
He says, is it a dangerous distraction to talk about targets when it is budgets that count, i.e. the rate of reduction? If that makes sense.
Yes, okay. Yes, I understand the point, and it's an absolutely crucial one. Introducing that into a general talk is difficult for me without... You probably all the people in this audience will know the difference between the annual amount of emissions that we are generating and the total budget we have to spend in terms of billions of tons of CO2 and other greenhouse gases before we've run out of that budget and have 1.5 or 2 degrees. It becomes impossible. So I spoke then about the rate of reduction, because that's a concept which people find relatively easy to understand. Using up the carbon budget, I would say, is not as easy for the general audience to actually relate to. So I make a decision, and this could be very well the wrong decision when I'm giving talks, to focus on rates of reduction without talking about the notion of a carbon budget. But the intellectually robust way of approaching this is to say, we have 1 trillion tons or 500 billion tons of before we run out, and we're going necessarily to exceed our carbon, our temperature target. I mean, absolutely central question. This is a general presentation, and I don't address it properly. I'm going to talk about energy, though, for most of the rest of this presentation, rather than all the other things that we might want to talk about from the book, such as agriculture. And I am going to try to make the case for a radically different energy policy for the UK, and indeed other countries with large amounts of renewable resources available to them. What I'm proposing is that we move away from our current model of electricity generation to say, actually, electricity converted into hydrogen can provide us pretty much full decarbonisation of every single economic sector, whether it's steel making, fertilizer production, or whatever. So my proposed route is to continue to massively increase the amounts of renewable electricity generated in the UK, so that almost all of the time there is too much wind, too much solar to provide for our electricity. We therefore have a surplus. We don't have to worry about intermittency. And we use that surplus in the form of hydrogen to perform balancing services and to make sure that we have the access to an energetic molecule in the form of hydrogen, which can perform other tasks for us, which cannot be electrified. So that's the thesis in the rest of this presentation. Here's beginning with the detail. This is this year between the 20th of August and the 27th of August as an illustration of the problem that renewables face. No news here to anybody listening to this presentation. Renewables are intermittent, unpredictable, and unreliable. So the theory at the moment is we use as much wind and solar as we can, plus biomass and any other renewable sources we have available, to a small amount of hydro and so on and so forth. And where that's not enough, as it almost always isn't enough under current conditions, we supplement it by turning on gas-fired power stations. So gas acts as the complement to wind. And the reason I've chosen this period, from the 20th to the 27th of August, is we saw a massive variation in the amount of wind being generated in this period, and therefore also a massive complementary variation in the amount of gas that we needed to burn to make our electricity demand fulfilled. The highest levels of wind, as you can see, were on about the 22nd of August, but also on the 25th and 26th, when there were periods when wind plus solar provided almost all of our electricity. But on the 25th of August, there was very little wind. It's only 36 hours before the peak, later on the 26th. But that was the period of peak gas demand. Those are fairly typical weeks for windy periods of the year. Very unusual for August, but that's the kind of pattern that you might expect to see now or right through until March of next year, with winds springing up and delivering large amounts of our capacity. So let's look a little bit at the details of those two particular moments. One, when there was very little wind at 2100 on August the 24th, and gas provided 60% of our power. And August the 26th at 3 o'clock in the morning, wind provided, I think, the highest ever level of wind power available to the UK at 61% of total demand, and gas fell back to 19%. And the way that things operate at the moment, grid is very unwilling to take gas down below about 3 gigawatts because of the need for this complementarity in the face of an unpredictable wind availability even half an hour out. Not that unpredictable, but a bit unpredictable. So that's the way we run things at the moment. And in future, what the government currently is saying, let's get this, the right slide. What the government is currently saying is that it will run the system so that wind and solar continue to provide much of our electricity, but that gas-fired power stations with carbon capture and storage are always available to provide complementary power. So gas plus CCS is the central mechanism by which we make sure that electricity demand is provided. But under these plans, the average amount of renewable electricity coming into the grid never goes much more above than above 65%, which means we have to have a lot of gas, we have to have a lot of gas capacity to complement that, even if we continue to build a few nuclear power stations at the same time. Nuclear power stations actually make the problem more difficult, not less. So the strategy I propose that's different from that, very different from that, is to say, what about building 20 times as much renewable capacity as the UK has at the moment? We have about 22, 23 gigawatts of wind, about 10 of which is offshore. We have about 13 gigawatts of solar, and I'm proposing that we multiply that 20-fold. And even though electricity, renewable supply, of course, is highly variable, this huge expansion of electricity availability means that most of the time, perhaps all but a few hours a year, we have enough electricity for our electricity needs, even after we've decarbonized transport largely by switching to electric vehicles. and by increasing dramatically the use of electric heat pumps for domestic heating and for the heating of office buildings and buildings like your colleges, for example. Now, my proposal, and it's becoming almost a cliche in Northern Europe, apart from in the UK, is that temporary electricity surpluses should be stored in the form of hydrogen. Of course, that's a simple process in theory, but quite expensive in terms of energy losses currently. But electrolysis, we've known about for 150 years. Electrolysis is getting much more efficient. It's getting much cheaper, to the point where today we can hope for 80% conversion efficiency from electricity into the energy value of hydrogen. We can use some of the heat that comes off for low quality heat, low temperature heat purposes. And hydrogen and electricity is getting even more efficient at producing hydrogen. Now, so I'm proposing a renewables plus hydrogen economy in the book. No CCS, no use of fossil fuels whatsoever across the economy. First of all, we have to fully decarbonize electricity. And in the slides that follow, I produce a very, very simple model for why I think this will not only the best, but also the cheapest way of decarbonizing electricity. And I stress, I'm talking in this section just about the decarbonization of electricity. And then we'll move on very briefly to talk about the possible decarbonization of other sectors using hydrogen and electricity where necessary. So I have a very simple model at the back of my mind, and it's a complete distortion, of course, of reality. The electricity market, the electricity supply and demand situation is vastly more complicated than this. But I want to try to show why a massive expansion of electricity supply isn't necessarily a costly thing to do if we use low-cost renewable resources, which of course are offshore wind and solar are becoming all the time. But in this model, I propose an average demand of 36.5 gigawatts, which is very roughly the average for the UK, and hold that across the year. Every single hour of the year has exactly the same demand. And I don't think that's a simplification which ruins the effectiveness of this comparison. And I'm imagining a situation where wind, there's only one renewable source, and that's wind, and that cycles in a straight line or a sine curve between 0 and 100% capacity utilization. One day the wind is blowing, it's sufficient to mean that every single wind turbine in the UK is operating at peak capacity, and 2 days later it's nothing. Roughly the situation that we saw in August in those numbers there. The average wind capacity factor, I model, is between 45 and 52.5%. And it depends on how much new capacity we're putting in. Offshore wind going into the North Sea at the moment is operating probably higher than, will achieve probably higher than 52.5% capacity factors, although there's still some doubt about that. So the big Ørsted farms that are in planning, they are saying that they should be able to get 55%. Let's see whether that's achieved. The figures that have been released recently for the last major Dutch auction for offshore wind have suggested a figure of around 50%. I think we can do better on Dogger Bank than that. But therefore, the average wind capacity factor depends on the scale of expansion. The more we expand, the better capacity factor we'll get, because we'll be using better turbines in better locations. And I'm assuming that a wind to hydrogen conversion in electrolysis is roughly 80% efficient, and hydrogen back to electricity, if we want to do that, at 65% efficiency. And therefore, and I'm assuming no other use for the heat that's generated in those processes, and that the round trip efficiency, therefore, is around 45%. And most of the time, I say that, and people say, gosh, that's incredibly inefficient. We can't possibly make that a successful way to go. And then I say, well, you put a ton of coal into a power station, and typically, until recently, you get about 30% efficiency. We live with that without any problem. So I try to get around this. But right at the end, I'm just going to give you a few figures for why, in the end, this is still going to be, I hope, the right way to do it. So the current way of thinking about it, the government's model, for want of a better word, the Committee on Climate Change's model, the way we generally talk about this, is to run our system like this. 36.5 gigawatts constant demand for constant supply, demand for electricity, and supplied by wind and by gas and CCS in that alternating pattern, where gas always complements the availability of wind over time. So the simplest possible route. So I'm proposing something very different from that. I'm saying that we need approximately 90 gigawatts of wind. That's very, very roughly 90 gigawatts of renewables, forgive me. That's approximately 3 times the renewables we have at the moment. Not quite as much as that, but roughly that level. But the government only a couple of weeks ago said that it was intending anyway to push offshore up to around 40 gigawatts by 2030. Now, at that point, there's already too much electricity demand, much of supply, much of the year, if the wind is blowing hard. So, like it or not, the government is already moving from the point where it's just providing enough renewables capacity to cover the peak demand, to cover at peak the demand. And in this model here, I'm saying that most of the time we are going to have excess electricity supply, and we'll convert that electricity to hydrogen. Those pyramids above the green line. Below it, when we don't have enough wind, those few hours a year when we don't have enough wind under this scenario, we'll be taking that wind and converting it back to power, either through combustion in gas turbines, which are being converted to use gas, only 20% hydrogen at the moment, but GE, the biggest world manufacturer of turbines, is now talking about 100% hydrogen gas turbines by the later part of this decade. So we could either combust the hydrogen, which of course just produces water, or we could put it into fuel cells, large fuel cells, to produce power that way. Both of them roughly 60% efficient. No great difference between them. And if we've got gas turbines now, which can be easily converted to hydrogen, then perhaps that might be the cheapest way of doing it. That's not the central point in my argument.
We've had another question, just quickly. Sir David Mackay estimated that the UK's maximum renewable capacity was well below total demand. Is this view out of date?
Yes. Totally out of date. David and I debated this, and we differed. David, if I may, the man was a hero. That book has influenced everybody around the world. It's a fantastic piece of work. His numbers for renewables in the UK were deeply wrong. For example, he was postulating average efficiency of 10% of solar panels, when you can now achieve 17-18% on commercial solar panels, for example. His figures for the power density of wind were also out of date. That's because wind has got so much better, particularly offshore. And in a few slides down this presentation, I'll show a map of the UK with illustrative squares for how much space would be needed to provide onshore, offshore, and solar power sufficient to give us all the energy we need, not just electricity, all the energy we need, some of which will go into hydrogen, which will then be converted into synthetic fuels or be used in the manufacture of steel or fertilizer, for example. So with great respect to David Mackay, no, the UK is perfectly capable of generating all the renewable electricity that we could conceivably want. Very roughly, and we'll go into this in more details, my plan to 20 times multiply the amount of electricity we generate from renewables compared to today uses approximately 1/3 of the UK's shallow water exclusive economic zone. That is the area around the UK, which after the final transition date of 31st of December, the UK has the right to exploit for electricity. And that's unambiguous. That's not being debated like fisheries. So I think it's a perfectly manageable target. But thank you for asking the question. We should debate that more because David's views, David's numbers are still extraordinarily influential. Now, that was an unfair model, unfair on my hypothesis, because very, very rarely does wind go down to zero. In fact, I haven't seen it this year. There have been some very, very low wind days over the last week, but it's still been of the order of its 10% capacity or so. And a more realistic model is to swing between a few tens of gigawatts and 60 or 70 gigawatts. And in this model, I've assumed that we actually generate 85 gigawatts of electricity at peak, absolute peak, which will occur, of course, very rarely as well. Now, sorry, I put this in a spreadsheet. It's a little complicated, but the purpose of this was to say, look, if you play with these numbers and you use the sort of figures that I have been putting in these figures, you come up at the bottom of the page, which I can't quite see because it's got something on top of it, with very similar costs for all of the three alternatives I've proposed. One, the government's model, as I call it, where wind is just constantly complemented by gas, just meeting demand, where we put in 90 gigawatts, and where we go with a more reasonable figure for about 85 gigawatts for actual requirement for renewables. The crucial figure then, the crucial basis of this assumption is the cost of, levelized cost of wind, which I put in here at £50 per megawatt hour, which is now looking a little conservative. I created these numbers a couple of months ago, but recently the government itself has come out with numbers which show that wind and solar are actually now below that figure, or will be below that figure by the middle of this decade. The figure for gas plus CCS is now estimated at around £80 a megawatt hour. That's, of course, dependent partly upon gas prices, which are at the moment low, and these numbers, therefore, would actually be slightly lower than that at the moment. But over the long run, these are projections for the cost of gas plus full CCS, and costing the fact that roughly 10% of the CO2 produced in a gas-fired power station, even with the most effective forms of carbon capture and storage, is lost to the atmosphere. So there's a cost to that. But the crucial argument in favor of my plan is not necessarily that it's roughly the same cost or perhaps cheaper than going the government, what I call the government route of wind plus gas, is that it produces the amount of spare electricity that's necessary to fully decarbonize the rest of the economy using hydrogen. So we've talked briefly. Yep, indeed, Ben. Go ahead.
It says, why focus solely on hydrogen storage? In practice, it will likely be complementary to other technologies like lithium-ion batteries, e.g. for intraday variations, hydro storage, etc., based on context.
Yeah, indeed. Thank you for that. Sorry, I've simplified this to the maximum degree. Obviously, rationally, for short-term storage, it's better to use pump storage, conventional batteries, and my thesis in the book is that a lot of the intraday storage is actually going to be provided by the batteries in electric cars. So we have an electric car, it's sitting in the drive outside, its battery is full, the light levels are going down, electricity demand is rising, so typical October evening. I would be very happy to be paid to have someone take the electricity out of the battery and use it to meet peak demand, and then put it back in the middle of the night and refill the battery to 100%. And that absolutely is the way we're going to go for short-term storage. It won't work for the core problem that high latitude countries more precisely face, which is major variations in the availability of renewables, solar and wind predominantly, over the course of seasons, and similar variations in electricity demand. So we could run the UK economy entirely on solar. Sorry, in some parts of the world, it would be perfectly possible to run the economy on the basis of solar energy with battery storage overnight, because solar is reliable enough in some places to provide it, with the battery being used 365 days a year. If we were to try to do the same thing in the UK, after a windy day, we would have to have a huge number of batteries, and often a huge volume of batteries, many terawatts, 10 terawatt hours. But also we would have to store that energy for perhaps 6 months. A windy winter, and we won't need as electricity demand falls, we won't need it. So we need to store it in something where the economics can cope with the fact that it's only being used once a year. Batteries aren't very good at dealing with that problem. So yes, we need storage. I'd oversimplified this question to include short-term storage and indeed medium-term storage. We need pumped hydro to deal with unexpected variations in supply, the breakdown of links, interconnectors with the rest of Europe, and so on and so forth. But the vast bulk of storage, perhaps 90, perhaps 95%, in my hypothesis, is going to come from hydrogen. And this, when I wrote the book a year ago, was clearly an eccentric view. But the EU and the individual states, particularly of Northern Europe, are moving more strongly than ever towards a similar view. Germany's promised 9 billion euros as part of its 30 billion Green New Deal package. France has put in 7 billion, and Spain has gone for 10.5 billion euros. So all of a sudden, there's a major transformation. If we're going to build a carbon-free economy, these states are saying we need to use hydrogen as the vector for energy storage and for transmutation into other sources of energy, which we need to complement electricity. We cannot electrify everything. So the 4 key uses for hydrogen in this slide are for either, as we said, a fuel cell or a turbine back into electricity, or we can use it to replace natural gas for heating. I'll talk a bit about that in a second. We can use it for steel manufacture to replace coal. As I say, that's probably 8% of world emissions, not much in the UK, but it's very significant elsewhere in the world. And we've got the beginnings of a route towards full-scale replacement of coal and other fuels with hydrogen. It's being pioneered by the Swedish specialty steels company SSAB, which now has got its first pilot part using coal to direct reduce iron, that is to say, take the oxygen directly off the iron ore, leaving you something like pure iron, which can then go into something like an electric arc furnace to make steel in the same way as we currently recycle it. It's not just steel, where we can also use hydrogen for the manufacture of fertilizer, where the predominant ingredient is ammonia, which of course you know contains nitrogen and hydrogen, but where hydrogen is as it were, the energy vector. And lastly, and this is not being talked about enough in the UK at all, is the use of hydrogen as the key ingredient for synthetic fuels. And we'll talk a little bit more about that later. What do I mean by synthetic fuels? I mean chemicals which are chemically identical, as near as possible, to the energy-carrying liquids that we use in our economy, such as aviation kerosene for aviation, possibly diesel for very heavy lorries. I think everything else is going to be electrified. And other circumstances when we need fuel fuel in liquid form, because hydrogen cannot be made dense. Even liquid hydrogen doesn't have the weight or the space density that, for example, diesel does. So there are some circumstances, of which the most important is aviation, where hydrogen is going to have to be changed into a synthetic fuel. Now, I've postulated, the first section I looked at was looking at just replacing electricity demand using this renewables plus hydrogen route. I'm proposing in the book that it should actually, renewables plus hydrogen should replace all energy demand in the way that the last slide described. That means there are very few hours of the year when we don't have enough electricity, a tiny fraction, and very unusual. Though, and those cases that we can still convert hydrogen back to power, but mostly we're going to be using that surplus to create hydrogen for other needs. I talked briefly about one potential major use, which is replacing natural gas in the domestic heating networks with hydrogen. At the moment, that would be very expensive. There's no question it would introduce a significant premium to people's gas bills at home, or indeed at offices or other forms of building. So we have to make sure that we combine this, and this is a whole chapter in the book which I'm not discussing here. We combine it with a radical program of building refurbishment. At the UK has been very, very bad at improving the performance, thermal performance of its buildings. As I mentioned, we have some of the worst building performance in the world. We have over a quarter of our buildings, our domestic buildings, were built before 1914 with very limited attention to insulation. A radical program of street-by-street refurbishment, probably using external insulation, which is pinned onto the houses, is the way that I propose in the book that we should go. So, but that's a crucial need, a crucial use for that surplus hydrogen. And by the way, it's very easy to convert. It's very easy to make hydrogen boilers that replace conventional natural gas boilers in our homes. They aren't more expensive, or they'll be a trivial amount more expensive. They are as safe in all probability and as easy to maintain and use. So I talked a bit about the amount of land that we would need, land and sea that we would need to do this, to try and deal with the point that the questioner made earlier, that David Mackay is highly skeptical about the possibility of doing this. There is the space that we would need. I'm proposing something like 250 gigawatts of offshore wind. There's the space we would need, roughly, to have that. It has to be said that that square, in all fairness, goes slightly into the Dutch quadrant. That's a little mistake on my part. I put that square a little too far away from the coast. But as I said, it's still only using a third of the UK's shallow water, that is less than 50 meters deep capacity. Onshore wind, probably, well, you can cover a lot of Scotland with onshore wind. I put, therefore, the square up there. It's a large area, no question about it. But the point is that with wind, you can do a lot of things underneath it. It doesn't stop you. And in other words, in much of Scotland, there there is small-scale agriculture, of course, but nothing else. Relatively low population densities. We will need to build links from Western Scotland into the rest of the United Kingdom. Probably, by the time it's done, it'll have to cross a border between Scotland and the UK. But we've managed probably to negotiate a deal with EU already to secure the interconnections that we've paid for so far. I'm being imprecise here, but there was a concern until the deal was was done, the withdrawal agreement, that it wasn't clear how we were going to bring electricity via interconnectors into the UK, or indeed from the UK to Ireland, which is the predominant source of electricity for Northern Ireland at the moment. Solar, a relatively, I'm suggesting an expansion of, I think, 15 times in solar. I can't remember exactly, but that's a relatively small fraction of the amount of land, less than 2% of the UK's total land area. So I think David Mackay was using unfortunate assumptions, which are now outdated. He wrote probably that section in 2007, and the world has moved a great deal in that period. So that's my book. I'm very happy to answer any questions that anybody would like to ask, and let's engage in a conversation.
Thank you. Currently, we have no more questions at the moment, so I'll just give it a minute and see if anyone else has any questions that they'd like to ask.
Someone must want to argue for CCS. I mean, the argument for CCS, of course, is that we are probably going to have to develop CCS for cement manufacture. And it's very difficult to see how you can avoid piping off CO2 from the chemical changes that happen when cement is produced, the loss of CO2 from carbonates to make the oxide. So we're going to need to develop some form of CCS capacity. I argue in the book that since synthetic fuels do require carbon as they're hydrocarbons, so they require both hydrogen and carbon, we are going to need a source of carbon. The logical source for carbon is either collecting it directly from the atmosphere, or piped from cement manufacturing plants. Once again, 2-3% of world emissions, very important. We need to get that one right. Can't get to net zero without doing all of that.
Thank you. We have had a couple of questions. So we've had one saying, what's your take on floating wind, on offshore floating wind?
Thank you for that. I didn't deal with that in this very outline presentation, although it's in the book. My belief, and this could be wrong, it's really still too early to say, is that probably offshore wind will end up cheaper than fixed foundation wind. There are lots of places around Scotland where we will need floating wind if we are to fully use the resources we have. Scotland's keen on that. Scotland, for example, has been approached by Germany, as other countries have, as to whether it would be available to generate electricity for German hydrogen supply. And the evidence is that it's going to be possible to drive the cost down. There's only one small offshore floating wind farm in the world, and maybe slightly out of date, but the first one was off the coast of Scotland. There's a new one being proposed off the coast of Norway, and much of the wind availability off the coast of North America cannot be done on the sea is too deep. They cannot be done on fixed foundations. So the big impulse here is going to be the development of floating wind in the United States, and they probably will bring the price down to no more than onshore wind at the moment. Excuse me, not onshore wind, fixed foundation offshore wind.
Thank you. Building off that last mention of different locations, Bradley's asked that he said that a lot of this is very specific to the UK. Which parts would be transferable and what would need to be changed to very different locations such as India and China?
Well, right. Mostly it's replaced offshore wind with solar. Not in the case of China. There are good wind resources in various parts of China. India is not great for wind. There are parts of India, such as the Andaman and Nicobar Islands, where there is wind, but the subcontinent really is not great. So it has to be replaced by solar. But we'll drive solar down in places with a lot of sun. We'll drive solar down to below the cost of wind. I think that's unarguable. The International Energy Agency last week said that now solar is produced at prices which are lower than any electricity source has ever been in world history. My last book 4 years ago was about solar in particular, and I made the point then that the trend was pretty clear. Solar was going to be inside the tropics. Clearly, except for there are some wet areas, not everywhere inside the tropics. But when you get out 51 degrees north, for example, in the UK, you're probably going to be reliant more on wind. So the answer to the question is, a lot of the book is specific to the UK. We have specific problems: housing insulation. We have specific strengths, such as chemical engineering, which we can use for synthetic fuels manufacture. We import most of our food. So although a great deal has to happen to the world food system, much of that not necessarily something we have directly in our hands. Although personal view is after 31st of December, we're going to find ourselves making a lot more of our food than we did at the moment. But I argue in the book that the world as a whole, not just the UK, is going to have to move strongly towards a plant-based diet, and one that is not reliant upon industrial monoculture of grain. That is to say, thousands of hectares upon thousands of hectares growing wheat or maize. We have to move towards an agriculture that's less destructive of our environment, not just for climate change reasons, but for all the other environmental reasons, such as water pollution, biodiversity loss that we see around us. So much of the book is about the UK. It's aimed at a UK audience, but I think the lessons are often generalizable.
Great. We have a couple more questions. Which engineering technique do you think is the most in demand in the green industries? And then in brackets, energy, heating, etc.
Is this for career prospects?
It looks like it, I think. If you want, I can ask for clarification, and we can come back.
Would you just check that the questioner means
okay.
Where are the jobs going to be in 10 years' time?
Yeah. So in the meantime, I'll move on to a different question. What are the effects on marine ecosystems of large offshore wind installations? How could they be mitigated?
Well, the first sentence sounds as though it's a question. The second sentence sounds as though it's a statement. The evidence is that offshore wind in shallow waters, less than 50 meters, in general, has positive effects on marine ecology. There are examples where that's not been the case, but it is, I believe, possible to reconcile our wider ecological objectives with a very large-scale expansion of offshore wind. I've seen no convincing case that that is not true. Now, your questioner may have expert knowledge, which I don't have, but for example, you can create the base of the wind turbine becomes a very useful base for shelter and protection for marine animals and fish. Also, you get much less shipping traffic through it. Well, they're obviously not predominantly on shipping routes, but it also ought to be possible to minimize the amount of industrial fishing, which is the primary cause of the marine problems in large parts of the North Sea, for example. Bottom fishing, scraping the bottom of large areas of the sea in order to try to capture 100% of the fish in there. That's unbelievably destructive to the remainder of wildlife, the biodiversity down there.
Okay.
On the other one, Ben, just to go back to what I thought was the career question.
They've said career and in terms of demand for us to obtain net zero.
Okay. There might be different answers to those two, my guess, and this is only guess. I mean, who knows what's going to happen? But look, the UK is, in effect, the leader in offshore wind worldwide. We've tended to mess things up. We messed up onshore wind and gave it over to Denmark 30 years ago. Let's hope we don't mess this one up. But offshore wind is going to be the largest industry in the UK. I probably shouldn't have said that. That was too wide a statement. I'll take it back. But it's going to be an extremely important industry in 15 years' time. Not just manufacture, but maintenance and the digital activities that need to go on to make sure that offshore wind works properly. Now, at the same time, in the UK, we also need a very considerable expansion of digital control of our energy systems, whether it be at the trivial level, turning off machines that aren't being used when people go home at night. There are colleges that have tried in the past to to turn electric appliances off when there's nobody in the room in order to reduce consumption, that kind of thing. That needs to move on to a much larger level. We need to be very good at moving electricity and energy demand more widely from place to place and from time to time, temporal and location specific changes. That's going to be a thing. We're going to need a completely new agricultural system, in my view. And there's quite a lot about that in the book. So I'll let my ideology show. I think it's almost certain that the world will have to move to a near vegan diet in order to get to net zero. In the UK, this probably the second most important industry that I've spoken about briefly is improving the quality of insulation, on the thermal characteristics of our housing stock. We've done it very badly so far. It's been half-hearted, intermittent, unproductive. We are going to have to move to wholesale, street-by-street refurbishment. The engineering demands there are going to be enormous, both from manufacturing the materials that go onto the houses, but also making sure that it's installed properly. So that would be another industry which I think is almost certainly going to have to expand very dramatically if we're going to get to net zero. You know, roughly 25% of UK emissions come from households. Almost all of that is now from heating and a bit from air conditioning. We can't get anywhere near net zero if we don't address that problem.
Thank you. There's a bit more of a political question here.
Good.
Excess electricity and hydrogen. If the excess electricity and hydrogen option is more expensive, why not go with a cheaper route and use the difference to achieve more of the equitable outcomes for society?
I don't know. Sorry.
Up with just a statistic from Bloomberg New Energy Finance, outlining how that Bloomberg predicted or expected more than 150 billion in government subsidies for it to develop large-scale energy provision.
Is that 150 billion in the UK?
It doesn't say.
Okay. That sounds a lot of money. Let's say we try and achieve zero carbon by 2040. Let's say that's 20 years away. That's 7.5 billion a year. That is significantly. Let's think that is substantially less than 0.5% of UK GNP. So, and it goes without saying, I'm sure at the front of all our minds is that's a relatively small sum compared to what the government has spent on track and trace in the last 6 months. Let's not go into that detail. So the political question, sorry, the earlier question was, why go for renewables plus hydrogen when it would be it's actually approximately the same, to orders of magnitude, to the nearest decimal point is roughly the same to do gas plus CCS, because we don't have to do anything different. We haven't yet worldwide developed cost-effective CCS. People have been talking about it for the 15 years in which I've been working in energy. Virtually nothing has taken place. Scheme after scheme has been tried in the UK, and they've gone absolutely nowhere. So I've nothing ideologically against gas and CCS, but it does seem to me, and full CCS, getting everything and getting it stored forever, but it does seem to me that when we've got a working technology that's getting cheaper by the minute, wind, offshore wind, onshore wind, solar, why would we go into a route where substantial technical advances are still necessary? It seems to me that the argument is that we have a lead here. Things are getting better on renewable energies. How do we use that to decarbonize the entire energy system, not just electricity? And that's a large part of what my book was trying to be about. I've only obviously dealt with it in superficial detail here, but it's available in Blackwell's.
We have one last question, it seems. Do you think that COVID will have been a help or a hindrance to achieving these goals?
Yeah, it's interesting. I've been asked 3 times to write an article about this, and I find it very difficult to volunteer as a coherent view. On the one hand, it's clear that we've become more sensitive to the impact of environmental degradation. This virus, in the end, its root is the fact that we have deforested extensively and reduced biodiversity in large parts of the world. Obviously, it started in Asia, well, in all probability, and almost certainly started from bats, and those bats were moved because of deforestation, had moved. But do I see any sense in the UK government that it takes green issues more seriously than it did in February? Possibly. Has it organized? Has it shown itself capable of organizing a complex transition? Well, the reverse is true there. What it's demonstrated, I think, what the last 8 months has demonstrated as much as anything else, is a strong public sector is a necessary requirement for coherent action on any particular problem which is not susceptible to simple market mechanisms. Now, whether the UK is willing, with its current government or with the electorate, to say, okay, we need to rebuild and need to take decisions centrally. We cannot rely upon the private sector to deal with this most public of problems, whether it's virus or climate change, I think remains uncertain. I personally am not particularly optimistic about that. But on the other hand, every large company I talk to wants to do it anyway, despite what the inadequacies of the subsidy regimes, the regulatory regimes, carbon taxation that governments are producing.
Okay, thank you. There doesn't seem to be any more questions, so I'll just say thanks, Chris, for your talk and for answering those questions there. Next week we have Yun, and she'll be talking about modeling energy systems in Africa. Oh, we just have one last question, if you'd like to answer that. It says, wouldn't large investments in carbon capture and storage be a wise move holistically, given countries like China and Germany are still developing gas and coal plants? Gas and coal plants.
Gas and coal plants.
Yes.
How would us developing CCS plants in the UK help decarbonize China? And you know, China has now explicitly said that it views decarbonization as an economic opportunity, which it is. I'm not certain we can help them with that very much, personally. There's a society which has many, many failings, particularly from the human rights perspective, but is bloody good at organizing a response to crisis, whether it be virus or climate change. Biggest or second biggest solar park in the world opened there last week, 2.2 gigawatts. That's roughly a sixth of the UK's total capacity, developed over a course of 10 years. So the thing we can really add to China, I suspect, is expertise in offshore wind and a few other things. If we're thinking about export potential, I'm not certain that CCS provides it, because virtually no other country in the world is really looking at CCS deeply, with the exception of Norway. China, yes, it's talking about it, but it doesn't look as though it's central to decarbonization strategy.
Okay, thank you. Would you like to say any last words?
No, I've said I'm losing my voice. I've been shouting too much. Thank you very much indeed for the opportunity to talk, and
thank you,
and for the questions. Thank you very much indeed.